This talk is about how hard it is to find algebraic proofs. I'm Susanna Di Rizendi from the Czech Academy of Sciences, and this is joint work with Mika Goes, Jakob Nordstrom, Tony Petassi, Robert Robert, and Dmitry Sokolov. So let's start by defining the satisfiability problem. So here we're given a formula in canonical normal form. That means that we have variables and negation of variables, which we call literals, disjunction of literals or clauses, and the formula in canonical normal form is a conjunction of clauses. And our goal is to answer the following question. Is there a truth value assignment to the variables that satisfies all clauses in the formula? If the answer of this question is yes, then the certificate is simply an assignment to the variables that satisfies all clauses. And if the answer is no, then the certificate has to be some kind of proof of unsatisfiability, which I'll also call a refutation of the formula. Proofs of unsatisfiability can come in many forms. I'll start by defining the most basic, probably the most well-studied proof system, which is resolution. So here we have our formula in canonical normal form, and we can derive new clauses by this resolution rule. So if we have a clause C or X and a clause D or not X, we can resolve over the variable X and derive the clause C or D. Since this rule preserves satisfiability, if we derive the empty clause, which is unsatisfiable, we've proven that the original formula is also unsatisfiable. So let's see an example. So here we have the initial clauses of F. Now we can derive new clauses. For example, if we resolve this clause X or Y with not X or not Z, we resolve over the variable X. We'll derive the clause Y or not Z. Similarly, here we'll derive the clause not Z. Then we can derive the clause X or Y. And we can derive the clause Z. And finally, we can resolve not Z and Z and derive the empty clause. So this is a proof that the original formula is unsatisfiable. Now, there are two complexity measures that we're going to care about. The first one is the size of the proof, which is simply the number of clauses in the proof. So in this example, we have 10 clauses, so the size of this proof is 10. The other complexity measure is the width of the proof, which is the maximum number of literals in any clause. So in this case, it's 3. Now, a very important question in proof complexity is how hard is it to find proofs? So if I give you an unsatisfiable CNF formula, is it hard to actually find some proof of this formula? In order to formalize this question, Bonnet, Petassi, and Raz, they defined this notion of automatability. So for resolution, we would say we have an automating algorithm for resolution. If we have an algorithm that, given an unsatisfiable formula, outputs some resolution refutation of this formula. Now, an important constraint is that we want this algorithm to be efficient. We want it to run in polynomial time. But what exactly do we mean by polynomial time here? Because there are formulas that don't have polynomial size resolution refutation. So of course, there cannot be an automating algorithm that runs in polynomial in the size of the input that produces an output that's larger than polynomial, that's super polynomial. So by polynomial time, what I actually mean, or well, what Bonnet, Petassi, and Raz defined, is that we want polynomial not only on the size of the input, but also on the size of the smallest possible resolution refutation of the formula, smallest possible output of this algorithm. So I'll use the notation size res F to denote the size of the smallest resolution refutation of F. And in general, we say that a proof system P is automatable if there exists an automating algorithm for this proof system. That means that it outputs a proof or a refutation in this proof system, and that runs in polynomial time on the size of the input plus the size of the smallest possible output. Now, the big question is resolution automatable? Does there exist some algorithm that can find resolution refutations efficiently? I mean, this is what SAT solvers are trying to do all the time. So this question was finally completely answered by Atserias Muller just 2 years ago. And what they proved is that if resolution is automatable, then P equals NP. This was a major breakthrough result. But I think that in order to really appreciate it, we need to see a bit of the history of automatability. Here we have a hierarchy of proof systems. Just note that resolution is somewhere down here. Up here we have extended Frege. And the first non-automatability result was proven by Krychek and Plidlak, 98. They showed that extended Frege is not automatable unless RSA can be broken by polynomial size circuits. So this is a cryptographic assumption. This result was soon after extended also to Frege and TC0 Frege, and then using a stronger assumption to AC0 Frege. So the first non-automatability results were obtained for these stronger proof systems. Then for weaker proof systems, the first result was by Alekshnovnik and Razborov in 2001, and they showed that both resolution and tree-like resolution are not automatable unless the fixed parameter hierarchy collapses. But almost 10 years later, this was extended to polynomial calculus and Mostolen sets. And more recently, it was shown that both resolution and tree-like resolution are not automatable in slightly super polynomial time unless ETH is false. So this was the landscape of non-automatability before Atsarias and Muller. So let's see how Atsarias-Muller changed this landscape. So what Atsarias-Muller proved is that resolution is NP hard to automate. And soon after, this was extended to cutting planes by Gös, Korot, Merz, and Pitassi. It was also extended to resolution over KDNFs by Garlick. Then Bell showed that the result also holds for regular and ordered resolution. So it's a subsystem of resolution. Then there was also non-automatability result for tree-like resolution. And finally, this work, where we address algebraic proof systems, we show that Shirali-Adams, polynomial calculus, and Mostolen sets are all NP hard to automate. Now, in order to talk about our contribution, let's first see what the main ideas of Atsarias and Muller are. So in order to show that resolution is NP hard to automate, Atsarias and Muller proved this main theorem. So they showed that there is a polynomial time procedure that, given a formula F, produces a CNF formula here, which I'm calling A of F, that satisfies two properties. If F is satisfiable, then this formula A of F has a small resolution refutation. And if F is unsatisfiable, then A of F does not have a small resolution refutation. And indeed, it requires resolution refutations of exponential size. So we get a gap on the size of the smallest refutation of A of F, depending on whether F is satisfiable or unsatisfiable. From this main theorem, Atsarias-Muller follows very easily. So there's two-line proof. So assume there is an algorithm that automates resolution in polynomial time, calling this algorithm opt. And our goal is to decide whether F is satisfiable in polynomial time. So what we do is we first, in polynomial time, generate this formula A of F. Then we run this opt algorithm on A of F for a polynomial, large enough polynomial number of steps, so that if F is satisfiable, then opt will find a resolution refutation. But if F is unsatisfiable, it's impossible that it will find a resolution refutation because there is none of polynomial size. So in this way, we can figure out whether F is satisfiable in only a polynomial number of steps. So now all the work goes into proving this main theorem. To prove this theorem, we have to first define this polynomial time procedure, then show that it satisfies these two properties. So we have to prove an upper bound and a lower bound. And most of the work goes into proving the lower bound. So our first contribution in this work is to actually simplify this part of the proof. We make it more modular. Doing this, we can then extend it quite easily to polynomial calculus and Shirali-Adams. Then for Mostolen sets, we need a little bit more of work because we need to actually fix the upper bounds too. So let's explain first what this procedure is, and then we'll get into how we simplified this proof. This formula A of F is going to be a formula often called ref F, which encodes that F has a small resolution refutation. So F has a resolution refutation of size S, where S is some polynomial in the number of variables of F. Okay, so how do we encode this? Well, what does a resolution refutation look like? So we remember first we had the clauses of F, and then we had some other clauses. So here we're saying there's a proof of size S, so we have a total of S clauses. And now we need variables to actually say what these clauses are. So we're going to have some variables for each of these blocks. So the blocks are representing some clause in this purported refutation. And we'll have 2n variables for each block saying what is actually the clause in this position. So it's 2n because it's 1 per literal. So I'll have a clause for positive literal, negative literal. So if the variable for the literal not x2 is set to true, then we know it is in the clause. If it's set to false, it's not in the clause. Then we'll also have, for each derived clause, we'll have 2 pointers to going backwards somewhere that represents the 2 clauses that are used to derive this clause. And also have another pointer which says what is the variable being resolved. So which of the n variables is the one being resolved. So now we need clauses for this formula ref f that actually encodes that this is a valid resolution refutation. So for this to be a valid resolution refutation, we need first that we actually derive contradiction. And the second thing is that every clause, every derived clause actually is derived by a valid resolution step. And this we can encode with some CNF. Okay, so this is the ref f formula. It's stating that there is some resolution refutation of size S. Now note that this can be done in polynomial time. In particular, we'll only have a polynomial number of clauses, and the width of these clauses are going to be rather small, just O of log n, because S is polynomial in n. Now, before getting into the lower bound part, I want to say something quickly about the upper bound. I won't have time to explain it in detail. It's rather simple, but just to give some idea of the intuition. So we have this formula ref f that is stating that there is a resolution refutation of some small polynomial size s. And we know that actually f is satisfiable. So it doesn't even have any resolution refutation, let alone one of polynomial size. So the idea is that resolution is going to somehow reason about this. So it will have some satisfying assignment for this formula in mind and use this to show that ref f cannot encode a valid refutation of f. So just to give an intuition, let me explain how I would prove to you that this cannot be a valid resolution refutation, and this argument that I'm going to explain is formalizable in resolution. So if you told me that you actually have a resolution refutation of size S for a satisfiable formula, and that you could actually write it down here on these S clauses, I would start by asking you, okay, do you actually derive contradiction? And you would say, well, yes, in the end, I derive contradiction. So then it's okay, from what clauses do you derive contradiction? Oh, well, from these 2 clauses. And you'll point me to 2 clauses. And then since I have some satisfying assignment to the formula F, I know that at least if this is a valid derivation rule, this satisfying assignment cannot satisfy both clauses. So there's some clause it doesn't satisfy. Let's say this one. Okay, so now I'm going to ask you, how did you derive this clause? And again, you'll point to some other clauses. And again, there will be some clause which I know is not satisfied by this assignment. And I can continue doing this, walking down the proof until the clause that is not satisfied by this assignment is actually an axiom. But my assignment satisfies all of the original clauses of F. So I just showed you this cannot be a resolution refutation. So this is the idea, and you can actually formalize this in resolution. Okay, so this is for proving the upper bound. Now for proving the lower bound, we want to show that if F is unsatisfiable, then ref F requires resolution refutations of exponential size. And this is the part of the proof that we simplify in this paper. And this simplification comes from a reduction. So we show that we can actually reduce pigeonhole principle to this formula ref F. And the way to do this is that instead of viewing RefF as this long resolution reputation, we actually view it in layers. So we have n layers, and we can pretend this is a resolution reputation by embedding pigeonhole principal instances in between layers. This is the intuition. This is formalized by a notion of reduction. And from this reduction, we get a width lower bound for RefF of S over n squared. Now, if you want to know where this comes from, we have S over n lower bound for the width of pigeonhole principal, and then we'll lose an extra n factor because of the number of layers, because this reduction is not super efficient. It actually loses this n factor. From this width lower bound, there are several ways to get a size lower bound. One is the well-known Benson-Wigderson theorem. In order to apply this, we need S to be a large enough polynomial, so something like n to the 6 would be enough. Another way to get a size lower bound from a width lower bound is by lifting. I won't really explain what this is, but you modify the formula in some way that actually gives you this lower bound. So for this, choosing as larger than n cubed would be enough. I'd like to mention that this lifting technique is similar to the relativization technique that Otserias and Muller use. And just one observation, that if you actually do lifting or relativization, you have to make sure that the upper bound still holds, because you're actually changing the formula. Okay, so this is how the lower bound is shown. And this lower bound also holds for Nussdeulen-Satz, polynomial calculus, and Shirley-Adams. So this almost implies this result for all these three proof systems, except for Nussdeulen-Satz, we can't prove the upper bound for this RefF formula, and perhaps it doesn't even hold. So we have to slightly change the formula. So we actually define this tree ref formula, which encodes that F has a short tree-like resolution reputation. And then the lower bound works in the same way. We can reduce pigeonhole principle to this tree ref formula when F is unsatisfiable. And for the upper bound, we can actually do a reduction in the other direction. We can reduce tree ref F to this end of line principle whenever F is satisfiable. And this end of line principle is known to be easy for Nussdeulen-Satz, so we can get an upper bound for Nussdeulen-Satz. So this is how we obtain our main theorem. And from this, we get the NP hardness of automating all these proof systems. So going back now to that landscape slide, there's one thing that you might have noticed. So there's this sum of squares proof system, which is stronger than Shirley-Adams and stronger than polynomial calculus over the reals, for which we do not have any non-automatability result. So this is important open problem. Okay, so now take home message. In this work, we simplified the proof of Otserias-Muller by using this reduction to pigeonhole principle. With this, we were able to generalize the non-automatability results of Otserias-Muller to these algebraic proof system, Nussdeulen-Satz, polynomial calculus, and Shirley-Adams. And there's many open problems. So as we mentioned now, sum of squares, can we prove non-automatability of sum of squares? There are other proof systems that we can possibly improve their non-automatability result. So this would be bounded depth Frege. Can we actually show that it's NP hard to automate bounded depth Frege? Or even res k for larger values of k, or tree-like cutting planes. So there are other proof systems for which we still do not have their optimal non-automatability. Then there's the question of weak automatability. So for example, for resolution, we would like to know if you're allowed to run in polynomial time on the size of the smallest resolution refutation, can you find the refutation in a possibly much stronger proof system? So far, what we know is if we go back to this landscape, we know that we cannot find refutations in Shirley-Adams, polynomial calculus, cutting planes, but not for all proof systems. So perhaps we could find an extended Frege refutation in polynomial time on the size of the smallest resolution refutation. So this is completely open. And that's it. Thank you.